Welcome back, students. This is the session 4 from the chapter of circular motion, and the topic is derivation of centripetal force and centripetal acceleration. In fact, we will be first of all deriving the formula for the centripetal acceleration. So once we derive this centripetal acceleration, we will get the value of the centripetal force. So here, in order to uh, cut short the time, I have already drawn one figure here in which an object is moving in a circular path as indicated by these arrows, and I have taken A as the bottommost point of that object, and B is another point on this circular path which is very close to A. Now let us first of all consider that consider that the mass of the, let's say, body is m. The radius of this circular path is r, and this object or this body is moving in this circular motion with a uniform tangential velocity, say v. Uniform, linear, or tangential velocity, linear or tangential velocity is v, small v. Here I have considered that here A and B are very close to each other. A and B are the position of this object, where A is the bottommost position of this circular path, and B is the position of that body or object after a time t. And these two points, they are very close to each other. So theta will be very small in this case. Since A and B are very close to each other, therefore this theta will be very small in this case. And if theta is very small, then sin theta will be equal to theta, will be approximately equal to theta, and cos theta will be approximately equal to 1, because you know that cos 0 is equal to 1. So since theta is very small, therefore we can consider cos theta to be approximately equal to 1. And since theta is very small, so that sin theta can be considered approximately equal to theta. Now consider this point A. So at the point A, this body is having the horizontal velocity, horizontal component of the velocity. So at the point A, this body is having the horizontal component of the velocity which is equal to v, and this is also the tangential, or you can say the linear velocity. And at this point, the vertical component of the velocity is 0. So the vertical component of the velocity is 0. Now at the point B, since this angle is theta, therefore this angle I have already marked So this angle, that is OBD, this will be also equal to theta. Now this V is the tangential velocity. Therefore, this angle OBC, this is equal to 90 degree. So if this is equal to 90 degree, and this, if this is theta, then this will be equal to 90 minus theta. Now this V sin theta and V cos theta. V cos theta means this is the horizontal component of this velocity V, and this is the vertical component. So this angle, that is DBE, this will be equal to 90 degree. If this is 90 and this is 90 minus theta, so this angle, that is CBE, this is equal to theta. Now if this angle is theta, then the horizontal component will be equal to V cos theta, and the vertical component will be equal to V sin theta. So at B, horizontal component is equal to V cos theta, and the vertical component of the velocity, the vertical component of this tangential velocity is equal to V sin theta, and the horizontal component of this tangential velocity is V cos theta. Here we have considered that this body is moving with a uniform tangential velocity or the linear velocity, which is equal to V. So now let us, I will write all these small points here. That is, mass of the body is equal to m, the radius of the circular path is r, and the uniform tangential velocity is equal to V. Since theta is very small, therefore sin theta will be considered approximately equal to theta, and cos theta will be approximately equal to 1. Now let us consider the acceleration of this body in the horizontal direction and in the vertical direction. So the acceleration of the body in the horizontal direction will be this will be equal to this V cos theta minus V cos theta, because acceleration is the change in velocity divided by the time interval. So V cos theta minus V, and the time interval is t. That is, this object moves from A to B in time t. T is the time taken by the body from, it is the time taken by the body to move from A to B. Okay. Now, since theta is very small, therefore cos theta will be approximately equal to 1. So this can be written as V minus V upon T, or we can say it is 0. So the acceleration of this body in the horizontal direction becomes equal to 0. Now let us calculate the acceleration in the vertical direction. So the acceleration in the vertical direction will be equal to V sin theta. Now in the V sin theta minus 0, because the vertical component of the velocity at A is 0. So V sin theta minus 0 upon T, and this is equal to V sine theta upon t, and this is equal to, since theta is very small, therefore sine theta can be taken as theta, so this is equal to V theta upon t. And we know that omega, that is angular velocity, is equal to theta upon t, where theta is the, what is this theta? Theta is the angular displacement. So angular displacement divided by this time interval, so this is equal to omega. So V is equal to, this V theta upon t is equal to V omega. So the centripetal acceleration in the vertical direction becomes equal to V omega. So the resultant acceleration of the body will be equal to under root of this V omega square plus the square of the horizontal component, but the horizontal component is equal to 0. So square of the horizontal component, that is 0 square. So ultimately what we are getting is V omega is the resultant acceleration of this body. So it implies that resultant acceleration or the centripetal acceleration is equal to V omega. Now we also know that V is equal to R omega, as we have studied in the previous sessions. So from here I can substitute the value of omega. Omega will be equal to V upon R. So here I will be putting the value of omega as V upon R. So V upon R. So this becomes equal to V square upon R. Now this is the resultant acceleration is equal to V square upon R, and this is the centripetal acceleration, and this acceleration is directed towards the center. The direction, okay, that is this centripetal acceleration is equal to V square upon R, and this acceleration is directed towards the center. And because of this acceleration, a centripetal force acts on this body, which is given by the centripetal force on the body is equal to mass of the body into the centripetal acceleration, which is equal to V square upon R, which is equal to mv square upon R. So the centripetal acceleration on the body is equal to mv square upon R, and this centripetal force, the centripetal force on the body is equal to mv square by R, and this centripetal force is directed towards the center. Okay. So we have been able to, first of all we have derived the equation for the centripetal acceleration, which is equal to V square upon R, and since the centripetal force will be equal to, that is mass into acceleration, that is equal to mass, m is the mass of the body, into this centripetal acceleration, which is equal to V square upon R. So finally we have been able to derive the equation for the centripetal force also. So this is one of the easiest method of deriving the equation for the centripetal acceleration and the centripetal force. And in the next session, that is in the session number 5, I will be taking up a couple of questions based on what we have studied in the previous sessions from this chapter. So thank you very much for joining this session again, and have a nice day. Bye.